the idea, which is very widespread, I believe, in cosmology still, that there's some kind of crisis because we're faced with some situation where people think it makes sense to say, hey, here's what I'm worried about. The universe as it presents itself to us is highly improbable, is highly unlikely. The first thing that everybody ought to be saying is, that's a funny thing to say. It must be that you're getting your ideas about what's likely and what isn't from something in some other way than looking around at what happens in the world. Okay, that you think you have some a priori idea about what's likely and what isn't, or you have some divinely revealed idea of what's likely and what isn't. You have something other than an empirically founded idea about what's likely and what isn't.
Hello, my yeastlings. This is Mother Goose, Robinson Earhart, and Pins, the lovely podcat, here with the introduction to a tremendous episode, an installment in this Robinson's podcast, Multiverse Adventure. And this is episode number 106, and it is with David Albert and Sean Carroll. And if you don't know them, David is the Frederick E. Woodbridge Professor of Philosophy at Columbia University and director of the Philosophical Foundations of Physics program in the singular at the same. And he is a prior guest of Robinson's podcast, having appeared on episode 23 with my friend Justin Clarke-Doane, number 30 by himself. We talked a lot about the philosophy of time. And then episode 67 with Tim Maudlin, who is also totally terrific. And then Sean, on the other hand, is Homewood Professor of Natural Philosophy at Johns Hopkins. And he's also the host of Sean Carroll's Mindscape, which is a terrific show. I don't think I'm in the wrong saying it is the best philosophy/physics podcast. I mean, though he covers all sorts of other things as well. Sean is a terrific communicator, teacher, philosopher. I'm not a physicist, so I can't judge as well, but I have the sense that he's a very, very good physicist. And his show, Mindscape, really heavily influenced the birth of my own as well. But again, in case you don't know them, David and Sean, as I've already said, they're rare breeds. They're philosophers who are physicists, physicists who are philosophers. And so naturally, in this episode, we get into some of the philosophical concerns at the foundations of physics. And in order, we talk about the many worlds theory, not too many words, just two, the many worlds theory of quantum mechanics, the fine-tuning or apparent fine-tuning of the universe for life, and then the possibility of Boltzmann brains. And Sean and David have both written about these topics, and there are links in the description to some of their work here. Most recently, Sean's book, The Biggest Ideas in the Universe. But still, just by way of introduction, I will comment a bit on what these topics are. So first off, the many worlds theory of quantum mechanics, also known as the Everett interpretation, named after the physicist Hugh Everett, is special for a number of reasons. And the two that come to mind right now and that are most important for the conversation that you're hopefully about to listen to are that despite the randomness and indeterminacy often associated with quantum mechanics, the many worlds theory is entirely deterministic, which raises philosophical questions for David because it seems to rule out familiar understandings of probability. And then on the other side, and much more peculiar to me, I'm in the minority here because this doesn't perturb Sean or David in the slightest. It's a feature rather than a bug. Is that, as the name implies, well, maybe not the name, but the theory. The many worlds theory entails that there are an infinite number of parallel universes that are continuously branching with each quantum event. And I find this troublesome, but that is just from my everyday natural intuitions about what the world should be like. And as I'm sure David or Sean would say, and I think Sean says something to this effect, in the episode, it really doesn't matter what I think the world should be like. What matters is what it in fact is like. But anyway, this leads into our discussion of the fine-tuning of the universe for life. Again, I should say apparent fine-tuning because there's obviously debate here. And which on the one hand, this might be accounted for by appealing to a multiverse type scenario in which all possible configurations of the laws of physics, the different assortments of particles, the early conditions of the universe are instantiated, though this multiverse scenario emerges more from cosmological, sometimes string theoretic concerns rather than the quantum considerations we talk about in the first half of the episode. But then another major point in the discussion, or in discussions of fine-tuning in general, which I just indicated, is entropy and the configurations of, or configuration of, the initial stages of the universe. Now, this naturally, if you know what I'm about to talk about, leads to Boltzmann brains, which more generally are theoretical brains, though, as Sean points out, they could really be any macroscopic configurations that could arise spontaneously due to quantum fluctuations on the one hand, or the random motion of matter in the assumed infinite period of thermal equilibrium to come in the universe's future history. But the problem here is that since these should apparently arise much more often than natural observers like you or me, I hope, it seems like we ought to believe that we are ourselves Boltzmann brains, but something goes very wrong here because, as Sean and David would have it, it's just very backwards to be in a position where we should be assuming that we are Boltzmann brains. So David has an upcoming book, acrobatic podcast, called A Guess at the Riddle, that you might want to pre-order. There's a link in the description. Go to Sean's website, preposterousuniverse.com. He's also on Twitter at Sean M. Carroll. And as I mentioned, his latest book is The Biggest Ideas in the Universe, which was terrific. And David and Sean also have a terrific conversation on the Mindscape podcast, and there's a link in the description to that as well. But just if you're not listening to Sean's podcast, you're making a very, very big mistake with your time. And last but not least, likes, subscribes, comments, all extraordinarily helpful. And now, thanks for putting up with that introduction. Without any further ado, I hope you enjoy this conversation as much as I enjoyed having it with David and Sean. In my episode on the foundations of quantum mechanics with David and Tim Maudlin, we began with the idea of superposition and how different quantum theories accounted for it. But since that was close to 50 episodes ago now, I'd like to start briefly with superposition, wave function collapse, or lack thereof, and in particular how the Everettian theory accounts for the phenomena. And Sean, since you're our resident many worlds proponent, would you be willing to do the honors?
Sure. And in fact, I can kind of reveal that being an Everettian, I don't love the word superposition, to be perfectly honest, because I think it's pointing us in the wrong direction. It's perfectly okay. Everyone uses it. I use it all the time. Don't feel bad. But it does push us away from what I think is the underlying reality of the situation. You know, in classical mechanics, if we have a particle like an electron, it has a position and it has a velocity, and we could measure those as accurately as we want to, and we use those to predict what happens next, and so on. In quantum mechanics, let's try to be not too judgmental about what the final version of quantum mechanics is, but we describe the electron in terms of a wave function. And the wave function assigns a different complex number to all of the different positions that we could measure the electron to be in. And then the mystery of quantum mechanics is that we never observe this wave function. We say that the wave function tells us what is happening when we're not looking, but when we look, we always see the electron at a certain position. So one way of thinking about the wave function is it is a combination, a superposition of all possible different measurement outcomes for this observable we're looking at, in this case, the position. So for every single position you could see the electron in, there's a value that the wave function has, and that's just psi of x, the Greek letter psi attached to x. So if in this way of talking, we think about the wave function as a superposition of every different possible measurement outcome for the position. The reason why I don't really like that is that it's putting measurement outcomes front and center. I like to put the wave function front and center and then derive the measurement outcomes from them. But, you know, in the real world, we all start thinking classically, and we have to upgrade ourselves to quantum mechanics along the way.
Maybe I can, and this is just to reinforce what Sean was saying, not to in any way dispute it, because I think I'm pretty much on the same page. But just, how shall I put it? To get more of a historical idea of how such talk, seemed, of how that could have seemed a reasonable way to talk. You know, you think of experiments like the double slit experiment or the neutron interferometry kinds of experiments. We have situations where we're used to thinking classically that there's one thing or another thing. There are two, say, mutually exclusive things that we're used to thinking an electron could be doing in those circumstances. It could be passing through this slit in the screen with two slits in it, or it could be passing through that slit in the screen with two slits in it. And we find that at least thinking it through naively in accord with our classical intuitions, we get behaviors when the electrons run into a fluorescent screen on the other side of these two slits. We get behaviors which we don't know how to associate with the claim that it went through slit A, and which we don't know how to associate in any coherent way with the claim that it went through slit B, and which we don't know how to associate in any very straightforward way with the claim that it went through both slits, in the sense that it's a split in half, and one half went through one slit and one half went through the other slit. And we don't know how to associate it with a claim that it went through neither slit. And so something very mysterious is going on. Something very strange is going on, which, because of the extent to which we were anchored in these intuitions which instructed us that asking which slit it went through was a reasonable question to ask, produced talk like this talk about superpositions. I don't know if what I just said was more helpful or unhelpful, but there were situations. Maybe the part of it to emphasize is this: people were confronted with situations where, if you asked yourself which slit it went through, did it go through slit A or did it go through slit B, the behaviors you were seeing didn't look like they could be explained by either of those conjectures, okay? And that's why a name for what people were thinking of as an additional option was invented, that it was in a superposition of going through slit A and going through slit B.
So you're on the same page as Sean in that you're also not in favor of using the word superposition. So this is there are certain kinds of conversations in which it might be useful to use this term. There are certain kinds of conversations in which it might not be useful to use this term. Sometimes it's just a helpful way of indicating to a listener what kind of mathematical form of a wave function you happen to be thinking of at that moment. It's a superposition of position states. It's not a superposition of momentum states. I don't have a big campaign there against the word superposition, but I don't find anything that Sean just said in any way objectionable. Well, then maybe we should move to the things that you might find more objectionable. So, Sean, where does the many worlds theory fit into the motion of the electron as described in terms of the wave function?
Well, the other thing we really have to get on board, it's not just superposition, but that's important. But the other thing is entanglement. And that's absolutely crucial to the entire story. And entanglement was this feature of quantum mechanics that was kind of implicit from the start, but it was really emphasized by Einstein, Podolsky, and Rosen in their famous EPR paper in 1935. And the basic idea, the way I like to think about it is, if you have two quantum mechanical systems, like two particles, two electrons, then the way that quantum mechanics describes them is not separately for system one and system two. There is a single description for both of them at once. There is not a wave function for electron one and a separate wave function for electron two. There's one wave function for electron one and electron two as a combined system. And that allows them to be entangled. If you want to think of the electrons as being in a superposition, then that superposition has to take into account what both electrons are doing. So famously, electrons have spin, and they could be spin up or spin down. Maybe a single electron is in a state where you don't know what the measurement outcome is going to be, spin up or spin down. Maybe the second electron is also in such a state, but they're in an entangled state where if one is measured to be spin up, the other is going to be measured spin down and vice versa. And then there's a long discourse that Einstein, Podolsky, and Rosen actually cared about, trying to leverage this into a belief that quantum mechanics could not be a complete theory. But let's put that aside. I'm not really, we're not here to get into that probably. But the point is that entanglement means that this wave function we're dealing with is not a field in the ordinary sense, like the electric field or the magnetic field. Those are fields in the sense that they take on a value at each point in space, okay? Each point in space and time, if you want to put it that way. But the wave function is not a function of space. It's a function of the whole configuration space of whatever system you're looking at. If it's two electrons or two spins, but also if it's the standard model of particle physics with all the fields for every single particle, the entire configuration is what the wave function depends on. So Hugh Everett, when he was a graduate student in the 1950s, was given the thesis topic by his advisor, John Wheeler, quantized gravity. And he wasn't the only one to be given that topic. Wheeler was just into it at the time. And Everett sat back and thought about it. And he realized that the current dominant paradigm in quantum mechanics, the Copenhagen interpretation, started by saying you have an observer that is not part of the quantum mechanical description. The observer is a classical beast, and the observer is going to measure the quantum mechanical system, and then, as we said, you will only see one possible outcome, not the whole wave function. And Everett says, well, look, if the whole universe is my quantum mechanical system, there's no observers outside. I have to be able to treat the observer as a quantum mechanical system also. So let's just ask the question, what happens when an observer measures the position of an electron? And let's just follow the Schrödinger equation, which is the equation telling us what happens. Let's not evoke any mysterious collapses of the wave function like Copenhagen says. Let's just do what the Schrödinger equation says. And everyone agrees on what the Schrödinger equation says. That's not the controversial part. What it says is that the combined system of the observer plus the electron evolves into an entangled superposition. And part of that superposition is the electron is at position X and the observer saw it at position X. Another part of the superposition is the electron is at some other position Y and the observer saw it at Y, etc. So for every single possible outcome, there's part of the wave function saying that's where the electron was seen by the observer. And Everett says, your worry is that can't be right. I've observed electrons, and I do not feel like I am in a superposition of every single possible outcome. And Everett says, you're right, you're not, because you are not the part of the wave function that describes you in all that superimposed glory. You are one of those possibilities. Each one of those terms in the wave function, the entangled superposition of you and the electron, those are all now different people, different observers, living their own lives henceforth. And so he doesn't change the formalism of quantum mechanics. He erases any extra formalism about wave function collapsing and so forth, and just says, if you just trust what the Schrodinger equation is telling you, it explains what a measurement is. It's just you becoming entangled with the system you're looking at. And then each version of you, there's many, many, many different versions of you, they're all real and they all saw different measurement outcomes. And that is what we now call the many worlds interpretation, which he first called the theory of the universal wave function. That was, there were many titles given along the way to his theory.
Sean, can I just ask a historical question?
Sure.
I knew, of course, that one of the ways in which Everett justified interest in this kind of interpretation was that it just wasn't going to be workable to position the observer outside of the system you were interested in. If the system you were interested in was a cosmological system, was the kind of system that general relativity is often applied to, so on and so forth. I hadn't heard before that this happened because Wheeler assigned him the problem of quantizing gravitation. Is that true?
It is true. I'm not making it up. But like I said, it wasn't just him. I was literally earlier today leafing through Peter Burns' biography of Everett. I ran into a guy. I gave a talk a couple of weeks ago, and I happened to run into an audience member who was friends with Hugh Everett back in the day. So that got me interested again. And yeah, Wheeler in the 1950s, Einstein's last public lecture before his death, public in the sense that, to a group of people, was to John Wheeler's class, general relativity class. And Wheeler had become interested in quantum gravity, and as was his wont, he was very organized about it. He assembled all of his graduate students and explained how maybe, we could think about this, and got them working on different aspects of the problem. Charles Misner was one of the grad students, and he did some technical things on gravitons. Everett was another one of the grad students, and he, latched on to this question of, what do you mean by quantum mechanics when you're the whole universe?
Amazing.
Yeah.
Thank you.
And by the way, Everett did say, that he thought he wasn't quantizing gravity in the thesis, but he did say, I think this will be very helpful when we do get around to quantizing gravity.
Yes, that I knew. Yes,
and that's the life I'm living right now. So I felt seen.
Well, maybe one more thing to get on the table before we look at some philosophical issues here is this term of art in the many worlds theorist lexicon, which is quantum decoherence, and how it relates to the branching of the many worlds that gives the theory its alternative name.
I can go first there, and then David can maybe fill in, because I'm the big fan here of decoherence and how the role that it plays in many worlds. I think, there's a step, the crucial step in Everett's argument that says, and we're allowed to consider all of these different parts of the wave function as separate worlds, right? And he gave it a justification for saying that, but it's a little bit different than our current justification. In fact, he even used the words, the environment, and he said that observers become entangled with their environment, but he just didn't develop the theory as well as it is now. It was in 1970 that Hans Dieter Zeh really started talking about decoherence, which is basically the idea that once you have a quantum mechanical macroscopic system, right, like something bigger than an electron that is in what we would think of as a superposition of different macroscopic arrangements, like a pointer pointing to spin up or spin down, or a cat being alive or dead or anything like that, it's instantly going to bump into the rest of the world, the photons in the room, the air molecules, etc., the environment, as we call it. And that is decoherence, the fact that macroscopic systems, and even some microscopic ones, very rapidly become entangled with their environment. And therefore, in the full quantum mechanical description, the part of the wave function where the macroscopic system is doing one thing, and the part where it's doing something else, because they've been entangled with different states in the environment, that's why they will never interact with each other ever again. That's the process called decoherence. It's what guarantees that we're allowed to treat these different parts of the wave function as different worlds.
It's you might think of this process of environmental decoherence as sort of what's erecting the barriers between these various different things that Everett is referring to, or that people in this tradition refer to as different worlds. And it's what makes it sensible, or it's a necessary condition of what makes it sensible to talk about them that way, as separate things that aren't going to affect one another, that aren't going to be visible to one another, so on and so forth.
And I'm sorry if this is a naive question, but is there a proposed sort of mechanism for the splitting or the branching of worlds that occurs with measurement? Or is that okay? There is.
I mean, it's the Schrodinger equation. It's not. It's just a matter of looking at what the Schrodinger equation is going to tell you happens, and you're going to get a branching structure out of the Schrodinger equation itself. This is what Everett initially noticed. There are going to be questions about why. So the branching structure you just get immediately out of Schrodinger's equation, and you get it. You get it without even considering the interaction of the system with its larger environment. It was that was supposed to be mysterious. That is, you get this branching structure. What the Schrodinger equation tells you is that you've got a superposition of one branch in which this electron spin was up and the observer saw it up, and another branch in which the electron spin was down and the observer saw it as down. That branching structure you get right out of the Schrodinger equation. There is a question about why we shouldn't be worried about these two branches interacting and becoming aware of one another in ways that we're not used to occurring in our laboratory life when we do such measurements. The explanation of that is what you get by including also the environment in the system you're considering. But once again, the mechanism is just the Schrodinger equation.
Now, David, then why on a prima facie level, since this seems like a neat explanation of a troubling problem and many of the familiar puzzles related to wave function collapse, why does this seem like an implausible view for you?
I mean, there are a bunch of things that are hard to get one's head around here, but the concern that most of the discussion has centered around is something that can be brought up very simply. What we're used to quantum mechanics giving us before Everett, what we're used to old-fashioned quantum mechanics giving us are probabilities for the outcomes of experiments, okay? And if somebody asks us why we believe quantum mechanics or anything like quantum mechanics, what we're going to cite what we're going to point them to is the fact that the frequencies of certain kinds of experiments, which we've repeated many, many times, are in good accord, amount to a good statistical fit with the probabilities for the outcomes of these experiments that quantum mechanics gives us, okay? And so we'd better have a way. It's not going to be an option for us simply to stop talking about those probabilities or something like that. If we want to have a story about why we believe quantum mechanics and what it is that we think quantum mechanics explains, and what it is that we think confirms quantum mechanics in our empirical experience, we're going to be talking about things like probabilities. Okay, so we're going to need on any way of understanding quantum mechanics that's going to be a contender, we're going to need some way of understanding what this probabilistic talk is about. Okay, on old-fashioned interpretations of quantum mechanics, it's about the stuff that probabilistic talk is usually about. Well, the world is indeterministic. Sometimes things happen this way. Sometimes things happen that way. The probabilities give you information about the frequencies that you should expect and about which frequencies are going to count as confirmatory of the quantum mechanical claims and which frequencies are going to count as disconfirmatory of the quantum mechanical claims. And very, very simply, what's puzzling prima facie about Everett's picture is that it's completely deterministic. Okay. The Schrodinger equation is a deterministic equation. We get these predictions that what happens when I do a measurement is exactly this splitting. Okay. Moreover, it's not just that it's completely deterministic. For example, classical mechanics is completely deterministic, and yet we speak of probabilities all the time in the context of classical mechanics. In statistical mechanics, we talk about probability distributions over initial conditions and so on and so forth. But in those cases, what gives the probability a chance to enter into the game in a coherent way is the fact that in the classical statistical mechanical case, we are usually ignorant of the microscopic details of the initial condition of the system that we're interested in. And we're very crudely speaking, I mean, we'll probably want to go into this in more detail later if we talk about foundations of statistical mechanics, but very crudely speaking, the probability talk is there to fill out our ignorance of the situation. That's also clearly not what's going on in the Everett case, okay? In the Everett case, even in cases where nothing relevant to the to the parts of the future development of the system that we're interested in isn't known to us, we still have these probabilistic things that the theory is giving us. And here, if you know those relevant things, you're simply not in any doubt about what any relevant feature of the future physical history of the world is going to look like. Okay, so so the initial puzzlement, the sort of initial observation that gives rise to what has turned out to be a very long and very interesting and circuitous and complicated and baroque discussion of the so-called problem of probabilities in Everett is this very simple observation. Where is there room for probabilistic talk here? What could this probabilistic talk possibly even be about? Okay, the theory, you know, if you consider an experimenter about to measure the z component of the spin of an electron whose x spin is definite, there's just nothing relevant about the future physical history of the world of which that observer will not be fully aware before she even carries out the experiment. There will be exactly one branch in which the z-spin is up. There'll be exactly one branch in which the z-spin is down. There will be an observer, for sure, who sees the z-spin up. There will be an observer, for sure, who sees the z-spin down. That's it, okay? It strikes one, so to ask under those circumstances, what's the probability that I'm going to see Z spin up, feels like you're looking at an amoeba that's about to divide, okay? And you say to the amoeba, what do you think the chances are that you're going to end up on the left, okay? Or what do you think the chances are that you're going to end up on the right? The amoeba says, I don't even know what this talk means. First of all, there's a kind of semantical question. I don't even know if the I that we're talking about here is something that survives this splitting process, okay? And even if it does, talk about chances here just seems out of place. I know for sure that there's going to be a half an amoeba on the left and there's going to be a half an amoeba on the right, okay? And there doesn't seem like any room. It doesn't seem like there's any room in a situation like this to be talking about chances. Now, mind you, and Sean will have a lot to say about this and is one of the major investigators who's produced a lot of what there is to say about this. This is the very beginning of the conversation, okay? This is a way of raising the question, okay? Since the question was raised, there have been many, many enormously interesting, enormously clever attempts to say what probabilistic talk might be about given this deterministic constraint. But it's easy in this way, at least to see, I think, why a question arises, why a worry initially arises.
Yeah. Sean, I want to ask you about your work on self-locating uncertainty and the Born rule, but really quickly, just in a sentence, I guess. My guess is you like the determinism of the many worlds theory, and for you, it's a feature, not a bug.
The universe doesn't care whether I like it or not, and I'm pleased that it's deterministic. But if it had been indeterministic, I would have lived with that.
Mm-hmm. But so, yeah, the relationship between objective and subjective probabilities in QM is quite involved. But I have the understanding that you think many worlds offers a particularly neat way of explaining probability. So enter self-locating uncertainty and the Born rule.
Yeah, I think actually, as a philosophical stance, I think that the opinions of the founders of a field should be irrelevant because we should move on from them. But again, I was fascinated to read in the Everett biography. He had all this like right there from the start. He often, one of the titles of his thesis along the way was Quantum Mechanics Without Probability. He had started his grad career interested in game theory and information theory and probability theory. It was only, in his second or third year that he moved into physics. And that's why he was so excited about it, because you could explain the apparent location of probability in quantum mechanics as a purely subjective thing, not as something that was based on frequencies. So David, everything that David said was right. He's very careful to say true things. I do not disagree, but I think that there's one little lacuna in the story that he told, which is that even though he was very careful to say there is nothing about the future development of the universe that is uncertain if we know the entire wave function, there are other kinds of uncertainty that are pretty relevant, and that's what's been recognized by Everettians since Everett. The way that I like to put it, following work I did with Chip Sebens at Caltech, is in terms of self-locating uncertainty. But if you think about that experimenter who's going to measure spin up or spin down along the z-axis, and they know with 100% certainty there will be a version of them that sees spin up and a version of them that sees spin down, all true. But there will also be a moment in the history of those two future selves where neither one of them knows whether they're on the spin-up branch of the wave function or the spin-down branch of the wave function. That's where the subjective uncertainty comes in. And I think that there's kind of two steps to recovering the ordinary understanding of the Born rule, which is the probability rule in quantum mechanics, probability is the wave function squared, et cetera, and fitting all that in. One is just answering the question David asked, which is, why are there probabilities at all? And I think that's very clear. I think I just gave you the answer. There will be a moment when you don't know where you are, and you need to put a probability on being on one branch or the other, or if you like, a credence, if you want to call it that. The other one is it sensible or necessary or advisable to use the Born rule when assigning those probabilities or credences? And there's two things. Number one, if you didn't want to be ornery, if you just wanted to follow your nose and do the obvious thing, the answer is obviously yes. The Born rule is obviously the right way to assign probabilities. It's just Pythagoras' theorem. It's very, very natural. It's a set of numbers between 0 and 1 that add up to 1 and are conserved over time, satisfying the axioms of probability, etc. But number two, you can try to be more sophisticated and try to make an argument why it is the uniquely rational thing to do. And that's where things get tricky. So I personally think I agree with Everettian critics that this is the single biggest worry about Everett, getting the probability rule right, getting the origin of probability and the actual rule right. But I think we've done it. I think we know what the answer is. I think that what is actually happening here is that it is truly a unique problem. In any other case where you're interested in probabilities or frequencies or whatever, in some sense, you can just count, right? You can just count the number of heads versus tails in the flipping of a coin, or the number of times that a spin is up or spin is down. And it's a different kind of thing you're doing in Everettian quantum mechanics, especially when the probabilities are not equal, when the wave function is the square root of 1/3 spin up plus the square root of 1/3 spin down. In a very real sense, there are two branches after you make that measurement, and you're trying to tell me I should act as if there's a 1/3 probability that I'm on one branch and a 2/3 probability I'm on the other branch. So whatever it is we're doing, it's not counting in the most straightforward sense. There are ways you can make it counting, but it's not quite straightforward. So I do think that the single biggest worry about Everett for me is not that I don't know where the probability rule comes from. It's that we're on sort of metaphysically shaky ground here. We are introducing ideas. We know what answer we want to get, right? We want to get the Born rule. And it's always easy to convince yourself that you've gotten the right answer for not necessarily the right reason. So I'm sympathetic to people who are like, you're really asking a lot of our abilities to reason for us to accept this. But again, I think that it's doable, and I think that it's the right answer. And there's, to me, so much more that is attractive about Everett in terms of physics that I'm willing to say that, yes, we have to get our philosophy better to really understand where all this is coming from.
So let me be a little bit of a curmudgeon here. So I want to back up a little bit, because I'm getting confused in this story earlier than Sean is getting confused. So forget about the senses in which this particular problem of self-locating probability is unique in the way that Sean was saying. That is, where the just number of counting the number of possibilities turns out not to be the right way to go. Let me see if I can say this a little bit carefully. I agree with Sean that that finding some situation where you're ignorant of but being able to put your finger on something that you're ignorant about is a necessary condition for probability talk to make sense. Sean, maybe he was talking just quickly, but Sean sounded like he was saying it's also a sufficient condition for probability talk to make sense. And that's a point where I'm already confused. So let's take a very simple case. A case that's not going to involve the complications, the additional complications that Sean was talking about that we encounter in quantum mechanics. So take some case like this. Captain Kirk is beaming down to the surface of the planet, okay? And he knows that the transporter is malfunctioning in a specific way. He knows, he steps into the transporter and he knows it's going to beam him down to the surface of the planet, but he knows that it's malfunctioning in the following way. When he gets to the surface of the planet, there are actually going to be two Captain Kirks standing side by side on the surface of the planet. One of them will be wearing a blue outfit and the other will be wearing a green outfit. And they both arrive on the surface of the planet with their eyes closed, okay? Which is what provides the interval of uncertainty that Sean, I think, rightfully thinks that we need in there, okay? So here's the deal. What I now know about the situation is I can feel the planet under my feet. I've arrived at the surface of the planet, but my eyes are closed, okay? And I'm wondering what to say about the question, what color is my outfit? Okay, good. I think it's definitely right, okay, that even though the situation is completely deterministic, okay, that is, Kirk knows before he steps into the transformer exactly what the future physical history of the world or the relevant parts of the world is going to be. He knows that there are going to be two of them standing on the surface. The one in the left is going to be in a blue outfit. The one on the right is going to be a green outfit. They're both going to have their eyes closed initially. Good. Now Kirk steps into the transformer, presses the button, feels that he's arrived on the surface of the planet, has his eyes closed, and says, I wonder what color outfit I'm wearing. And he's going to open his eyes in a minute and find out. There is definitely, notwithstanding the determinism of the overall situation, there's definitely genuine ignorance here. There's a long tradition of people saying, once you've got this ignorance, you've got a place where probability talk can get its foot in the door. And that specifically, it's obvious, and this is why I'm avoiding the complications that Sean was talking about that attend the more quantum mechanical case. Just in this case, there's a long philosophical tradition that predates the application of all this to the Everett circumstances. You know, this came up in famous discussions of the Sleeping Beauty problem and so on and so forth. There's a long tradition of saying, obviously, if I say to myself, what color outfit do I think I'm wearing? It's clear, it's somehow a priori clear, that the right thing to say is the probability that I'm wearing a green outfit is a half, and the probability that I'm wearing a blue outfit is a half. Because I know I'm one of these Kirks. I have no clue which one I am. That's then the probability. I already get really confused at this point, okay? And I'm not going to be able to, I sincerely don't have a fixed doctrine here. I'm just really confused. But let me see if I can evoke why I'm confused. Here's one way to put it. Somebody says, suppose somebody else says, no, that's not my theory. My theory is the probability that you're wearing a green suit is 0.9, and the probability that you're wearing a blue suit is 0.1. Okay. I don't know what sorts of experiments I should do. I don't know what sorts of measurements I should carry out in order to distinguish between those two claims. Okay. Usually, when we make probabilistic claims, we're dealing with a conception of probability which is in one way or another related to a frequency. That is, probabilities have consequences about frequencies. Probabilities make predictions about frequencies. Probabilities are explanatory of frequencies. And for reasons like that, frequency measurements can be confirmatory or disconfirmatory of probability claims. In a case like this, I can understand a sort of argument like, be reasonable. Why would you assign 0.9 to green? I mean, green and blue are perfectly symmetric in this situation. Fine. I can understand these sort of be reasonable arguments. What I don't understand is, suppose I've got some guy who says, you know what? I think the probability of green is 0.9. Why? Because I like green, and I think the probability of green is 0.9. And then the natural thing to say is, okay, we don't need to argue about this. Let's go out and do some measurements to settle it. I don't have any clue what those measurements would be. I don't know. So, for example, suppose we decided to repeat the experiment many times. Okay, Kirk beams down to the surface. He's got his eyes closed for a minute. Then he opens his eyes. He either sees a green suit or he sees a blue suit. Then he goes back up to the ship, does it again, yada, 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 yada. Okay, that's going to produce a lot of Kirks on the surface, 2 to the N Kirks, where he's been through N trials. Some of them are going to have seen this many green suits and this many blue suits. Others are going to have seen others. I don't know what we do with any of that information. I don't understand. I'm having trouble imagining what an experimental protocol would be, okay? That's going to end up with some written document that says our investigations have determined that under these circumstances, from frequency measurements, the probability of wearing a green suit is 1/2. I don't know what those experiments would be. I don't know what that measurement protocol would be. I'm completely confused by that. Here's another way of saying I think the same thing. Somebody says, so I'm standing there. So once again, the experimental setup is I consider myself at this moment after I've landed on the planet, but before I've opened my eyes. Okay. And I am, as Sean says, genuinely uncertain in that moment, notwithstanding the fact that the equations of motion of the entirety of the physical universe are completely deterministic. Good. I'm standing there and I say, okay, suppose I accept the reasoning of the people who believe in self-locating probability, and I conclude that the probability of the probability of a person in my position wearing a green outfit is 1/2. Then if we reason with probabilities in the usual way, and we know that there are actually 2 people down there, I guess you ought to conclude that the probability that both Kirks are wearing a green outfit is 1/4. Okay? But of course, that's not true. The probability that both Kirks are going to be wearing a green outfit is by construction of the situation 0. This is another way in which I don't understand how probabilistic talk makes sense. I believe this is just a restatement of what I was confused about in the first instance. Anyway, I don't want to go on and on here. I guess here is the headline. I've been confused forever, not just in connection with Everett, but much more generally. And this might come up if we later on discuss Boltzmann Brains, like Robinson was suggesting we might, and so on. I've been confused forever about what talk about self-locating probability is about, and what its relation to ordinary talk about probability is, and how it could be explanatory of certain aspects of our experience, and what kinds of frequencies I need to go and measure in order to confirm or disconfirm claims that the correct numerical value of the self-locating probability is such and such, and so on and so forth. I apologize. I've gone on way too long here. I'm puzzled about all this. And I'm sincerely puzzled. That is, it isn't as if it's obvious to me that this makes no sense. It's not clear to me how it makes sense.
So I would just say that you have to give up on the idea that probabilities are about frequencies at all. It is in the nature of subjective things that they are subjective. There is not an experiment that is going to tell you what is the correct subjective set of beliefs to have.
Are they about subjective frequencies, whatever that means? You mean they're not about frequencies? So say a little more.
I'm going to say a little more.
What are they about?
Yeah. They're about degrees of belief. They're about the best we can do in trying to understand what the situation of the world is around us. I mean, whether or not we should or not, I know you will admit that we do talk about probabilities all the time for things that are not frequency oriented. We talk about the probability someone's going to win the next presidential election. We talk about the probability that the dark matter is a WIMP versus an axion. We even talk about the probability of events that are in the past if we're not sure exactly what happened, because we have credences about them. And the point of view of the subjectivist on probability is that secretly all talk of probabilities is like that. I think that people will try to deny or try to separate out those kinds of probabilities exactly because they are not about frequencies. The subjectivist is just going to say, look, if you really thought, let's say that you were a fan of a formulation of quantum mechanics where there were truly stochastic collapses, right? And you could measure a spin of a particle and literally you don't know ahead of time whether it's going to be spin up or spin down, but the wave function collapses, and you do this many, many times. The subjectivist will say you're ignorant about something, namely the actual future history of the universe. And so you put a credence on different things. You're in a happy situation where you can get better and better at putting those credences on because you can do the experiment more and more times, but often you're not, and so be it. So that's what you're kind of stuck with. And the idea of asking which branch of the wave function am I on is supposed to be quite analogous to asking what are the laws of physics that I don't yet know. I give a probability that they're this way or that way. My credence that Everett is right is much higher than my credence that Bohm is right. But it's the same kind of uncertainty for people like us. Specifically in the Captain Kirk example, I mean, as David well knows, there are attempts to operationalize the idea that you should, in some normative sense, have a subjective credence that you're going to be 50-50, green shirt or blue shirt, for example, by betting, right? If someone really thinks I'm 90% going to be green, 10% going to be blue, you can win a lot of money off that person by betting 2-1 against them being green with both of their future selves.
In this actual Kirk case,
yes,
what's going to happen is not that you're going to win a lot of money. There are going to be branches in which you win money. There are going to be branches in which you lose money. There are going to be, once you repeat this many times, more branches in which you win money.
So are we talking about quantum mechanics or the?
We're talking about.
I was talking about your example exactly. I'm not talking about quantum mechanics.
I'm not talking about quantum mechanics either.
So there's no branches.
Oh, I'm sorry. Excuse me.
I'm going to win a lot of money in your thought experiment.
Well, wait. I don't understand. Suppose let's talk about the Kirk case. I say the chances of a green shirt are 90%, okay? And the chances of a blue shirt are 10%, okay? Good. So I bet on a green shirt, okay? Good. One of the Kirks wins the bet, the other Kirk loses the bet.
Right. So the bet I'm offering you is, if it's a green shirt, I give you $1. If it's a blue shirt, you give me $2.
One of them's going to win, one of them's going to lose.
But they'll both take the bet because they're both thinking there's a 90% chance they'll be green.
Right.
And I'm going to win $1 every time.
Oh, you're going to win. You'll be able to win. Yeah, that's what you mean. You mean the protocol is you make this bet with both of them. Okay. They both accept the bet, and each of them separately has to pay you if they. Yeah, that's definitely true. I don't understand how that. Let me put it this way.
The only non-exploitable credences they can have is that it'll be 50-50.
No. I didn't understand. It's whose interest. Okay, let me back up a little bit. Here's the puzzle. Usually, we take probabilistic claims to be explanatory of certain things, okay? Explanatory of the frequencies we observe in the world. Tell me a little bit more about these subjective probabilities that you're talking about. Are they capable of explaining things?
I'm just hesitating because I'm not quite sure what is capable of explaining things. They are part of your best strategy to make sense of the world you're in. So in that sense, yes. in exactly the same way that I have a probability belief, a credence, that if I jump out the window, I will fall down versus flying up. It helps me get through the world to think that I will probably fall down. It's probably a bad idea to jump out the window.
Well, okay, I don't want to get too much into the weeds here. Maybe let's go back to the scenario you brought up with the betting. Maybe it'll get us too far into the weeds, and then we'll just pull out. But let's try it one more time. I'm the guy who thinks there's a 90% chance of green. Okay, good. I bet on green. In one of the cases, I win. In the other case, I lose. In the case where I win, I say, this paid off. Great. Okay. And you say, but look, the other guy made money. Okay. That is, the bookie made money. Okay. You say, what do I care if the bookie made money? It worked out well for me. Okay. The other Kirk says, yeah, it didn't work out well for me. Okay. I'm now thinking that the right probabilities are 90% blue. Okay. Or something like that. But I don't understand. There is this guy on the left there is this guy who ended up being in a green outfit who won, who did very well. I don't know what you mean by saying these probabilities won't serve you well. Okay. You said won't serve you well, period, full stop. Well, I don't know. There's a guy who they served well. There's a guy who they didn't serve well. Okay. The assumption seems to be if there's one guy who they served well and there's another guy who they didn't serve well, I don't know what. That shows that they serve you well 50% of the time. I mean, I'm not sure how you go on from there. Suppose you repeat this experiment many times. There'll be one guy who wins every time. Okay. He says it worked great for me. Okay. Then there'll be other
we can short circuit this very easily. They were both Captain Kirk. They share a bank account.
No, I don't understand.
Let's assume that. Let's make that part of the setup.
If that's the protocol, and we want to maximize that bank account, then there's no question about how we do it. The question is whether setting things up according to that protocol, that they have one bank account, is the right way of answering a question of the form, what's the probability that I'm now wearing a green outfit? Okay. You're setting up. So here's something we agree on. As soon as a betting protocol is established, okay, about actual exchanges of money, pending this outcome or that outcome, once a protocol is established, once a protocol for accepting bets and paying bets off is established, and under exactly which conditions they're accepted and paid off and so on and so forth, then there's always going to be a best strategy, okay? But that best strategy is not going to go through some claim of the form, here's the probability I ought to assign at this moment to my wearing a green suit, okay? It's just going to be because of the way things actually come out in the physical world, okay? Like you were saying a minute ago, Sean, this is not about frequencies. This can't manifest itself in the physical world, these probabilities, because the physical world is completely determined, okay? That is, this self-locating strategy is a way of saying, David, I completely grant your point. There are no probabilities here. There are no frequencies here, okay? Good. Once that's been agreed to, it's not going to be cricket to then justify certain claims about these probabilities on the basis of how things are going to deterministically come out in the physical world. I agree. If the Kirks have a joint bank account, so on and so forth, then it's going to be an objective fact in the physical world that everybody knows in advance, okay, that the Kirk bank account, that the joint Kirk bank account is going to be depleted, okay? But that's, of course, the kind of occurrence which you've already said is completely irrelevant to this kind of probability discussion. The probability discussion is not something that can be manifest in objective occurrences in the physical world. That's what you meant by saying it's subjective, I think. I'm sorry, I'm conscious of getting way too far in. You should stop us, Robinson.
I'll say one more thing very briefly, and then I think you're right. We can move on. So I think the audience gets where we're coming from in both cases. But the point is, just like you just said, you tried to slide a little bit. You said there are no probabilities, there are no frequencies. But my whole point is that probabilities are not frequencies. They are only ever subjective degrees of belief. And the thing in the Kirk example, which is not the same as the quantum mechanics example, so that's a whole discussion. But the thing about that example is there is a unique set of credences to have that does not let you get exploited by any betting protocol, which is 50-50. And so, of course, you're allowed to have whatever subjective credences you want. But if you're the kind of sensible person who wants to align your credences to things that will make you happiest getting through the world in which you live, 50-50 is the way to go. And I think a similar spirit is true for Everett. But look, it's even harder in Everett since there's no shared bank account in that case. So and this is exactly why I admitted right from the start, this is the philosophically most tricky thing about the whole picture.
Anyway, for the general audience, the foregoing is a taste of how people get confused, or how I get confused about what's going on here. Right.
Well, very quickly, though, before we move on, just to make sure that the audience does indeed understand what's going on and that I do as well, I'm wondering if this is a decent summary of the high-level dispute here, that Sean retains probability by replacing objective probabilities with subjective probabilities, but you, David, have the sense that there must be objective and testable probabilities in QM, and that subjective probabilities qua Sean's self-locating uncertainties aren't testable or explanatory or based on frequencies as you think they should be.
I would say crudely that's right. I mean,
okay, crudely is good enough.
Am I allowed to put it just a tiny bit differently?
Yes.
And then I promise I'll shut up about it. Yeah, if these I take it that we need in theories like quantum mechanics probabilities that are objective, at least to the extent that that they can play the role that we're used to them playing in explanation, and that they can play the role that we're used to them playing in confirmation. Okay, that the probabilities being such and such commits you to claims about how things are going to go in the world, such that you can tell a story if somebody asks you, what are your reasons for believing that quantum mechanics is true? What is it that quantum mechanics explains? And what observations is it? What phenomena are there that we can point to that are confirmatory of the claim that the quantum mechanical probabilities are correct? Yeah.
Well, toward moving in a slightly different direction, something that surprises me about Sean and both of you, I guess, saying that probability is maybe the biggest concern with many worlds, is that I would have thought that the biggest concern is one of parsimony and simply just avoiding the inflation of your ontology to include this multiplicity of physical worlds. So
there's parsimony and there's parsimony. I mean, here I very much see the attraction of many worlds. Yeah, you got a lot of worlds there, but you have a beautifully simple theory. Okay. A beautifully simple set of laws. Okay. The laws aren't being mutilated. The beautiful symmetries of the laws aren't being mutilated with the addition of a collapse postulate. And even the ontology, there's also ontology and ontology. Okay. Yeah. You've got in some sense a huge ontology if you've got many worlds. Okay. But there's a separate question about how many kinds of fundamental things do you have? Okay. In Everett, you've just got the wave function. In other ways of solving the measurement problem that don't mutilate the mathematics of the wave function, like in bone, you have additional ontology in terms of particles. So there are various ways of judging how profuse the ontology is. And there are a lot of ways of judging it on whichever it comes out looking really nice.
So maybe just for a mathematical analog, I mean, piano arithmetic, for instance, is a really simple theory, same with ZFC, but the structures they describe are really rich, and that's a major plus, and that the theory is parsimonious. Okay. And then turning...
I don't think other things being equal, anybody would consider it an advantage of Everett that there are many worlds. We only see one. This is a balancing act, okay? The point is that other things aren't equal, okay? In order to get yourself one world, you need to, in one way or another, mutilate or add to the mathematics of the Schrodinger equation. You need to either mutilate it with a collapse or add to it with Bohmian particles and a guidance condition or something like that. So, I mean, other things being equal, which they're not, no, I don't think anybody would consider it an advantage of Everett that we've got all these worlds. We don't see them. We have no ordinary, everyday sorts of reasons for believing that such other worlds exist. If there were a way to get away without them, but be equally elegant, be equally parsimonious in terms of our theory, I'm sure I'm speaking for Sean here, everybody would be delighted with that. But the point is, there are various kinds of parsimony which you can weigh and balance against one another.
So what I'd like to turn now to is some larger, more cosmological questions. And in particular, I have the fine-tuning of the universe in mind. And for those who aren't familiar with this concept, it's the somewhat or very frightening idea that if the laws of physics, the nature of subatomic particles, or the early conditions of the Big Bang or the universe were just ever so slightly different, the universe would be utterly uninhabitable. And I'm wondering first, before we get into maybe the thermodynamical element of this, if many worlds at all relates to this fine-tuning of the universe. And my guess, if it does, is that while at some point the laws of physics might have been much more malleable, our branch of the wave function is one in which they developed in such a way as to be suitable for life. Is that at all? Or go ahead, Sean.
Yeah, I think that the traditional answer to this is no. These ideas have nothing to do with each other. When I measure the spin of a particle in many worlds, the laws of physics are the same before I do the measurement, and they're the same on both branches after I do the measurement. Now, having said that, I do think that the history of physics will look back 500 years from now and say, we really wasted some time in not exploring the consequences of many worlds long after the theory was proposed. I do think that in the framework of quantum cosmology, there are specific cases where, for all intents and purposes, it looks like the laws of physics are evolving as you make measurements and do branches, but they're not really changing. They're narrowing down to some very specific set of laws. And I don't think this has worked out. I'm writing a paper about it right now myself. There's another way of doing a very similar thing to try to connect many worlds to the cosmological multiverse, to say that, right here in this room, the wave function of the universe, which you can't actually observe, has a superposition of all sorts of different vacuum states of quantum field theory or string theory or whatever. all of this is very speculative and not necessary. My point is just that we don't know is the short answer, but the super short answer is that most people would say that the fine-tuning and the many worlds picture have nothing to do with each other. We're just poking at whether or not that's necessarily true.
So I know, though, that entropy, the second law of thermodynamics, does play a big role here. And I'll ask you, David, what this role is.
An enormous amount about the way we reason about the world, okay? About the way we make inferences about the past based on records or testimony or other kinds of evidence. An enormous amount about the way we reason about the world depends on a hypothesis to the effect that the entropy of the universe was once much, much lower than it is now. And the reason that this comes up in connection with discussions of fine-tuning is that these low entropy is that if you pick at random, where random means where random has a particular kind of mathematical definition, if you pick at random among among physically possible exact microstates of the world, low entropy states are ones that it is much, much less probable that a randomly chosen state would be among. Okay. Low entropy states correspond to a much smaller number of the possible physical microstates of the world than high entropy states do. Moreover, if you do a sort of naive calculation, consider the present macroscopic state of the universe, okay? Consider all of the possible microstates that are compatible with that macroscopic state. Then use what we think we know about the deterministic equations of motion, okay, to evolve the states that are compatible with the present macro state of the world forwards and backwards in time. If you did that kind of naive calculation, the result would be that states a long time ago are overwhelmingly more likely to be high entropy states than low entropy states. But if that were the case, all of our normal reasoning about what the laws of physics are, about what experiments were actually done on the basis of which we believe these laws of physics, so on and so forth, all of those would fall apart. All of our normal reasoning about the world would fall apart. So the whole structure of the way we reason about the world, the way we investigate the world, seems to take it for granted that we can depend on the claim that the entropy of the universe a long time ago was very, very low, okay? That is, the universe was in a state which by these normal canons of reasoning counts as very, very rare, very, very finely tuned, very, very improbable if you were just picking a state at random, okay? So this is an example of what people call fine-tuning problems of this kind.
Well, I guess starting from the beginning and digging in a bit deeper, what do the low entropic initial stages of the universe look like? I'm just trying to get a better sense of how you visualize them in a way that makes their highly ordered status obvious. Does that question make sense?
Yeah, they're very concentrated. They're all the material in the universe is concentrated in a very small region. Okay, that's the crudest and most obvious thing to say. If you have a gas in a box, okay, consider the following three possible macro states of the gas in the box. In macro state 1, the gas is all concentrated in a small region around the left-hand corner of the box. In macrostate number 2, the gas is all concentrated in a small region around the right-hand corner of the box. And in macrostate number 3, the gas is uniformly distributed throughout the box. The pressure throughout the box is uniform. The density throughout the box is uniform, so on. We have a really sort of tremendously important demonstration from Boltzmann from about 130 or 40 years ago, to the effect that the number of microstates, the number of exact microstates that's compatible with this macrostate that's uniformly spread out throughout the box is much, much, much larger than the number of microstates that are compatible with either of the macrostates in which the gas is more concentrated. Okay, so as a sort of zeroth approximation, situations in which the mass you're talking about is all concentrated in one region. I mean, of course, with general relativity, talk about spatial regions is terribly naive here in all kinds of ways that have to be corrected and blah, blah, blah. But just forget about that for the moment. We're doing a zeroth approximation here. Yeah, concentrated clumps of material, okay, correspond to much smaller numbers of possible microstates than uniformly spread out swaths of material. So that's the kind of thing we're talking about. The sort of state that one is used to associating with the Big Bang or with moments just after the Big Bang, everything stuffed into a small region, stuff like that.
I think I don't like this analogy very much. I mean, I get where it's coming from, but I think that it might be misleading in important ways because gravity is really, really important here. I mean, it's true that general relativity is the right way to think about gravity, but even in Newtonian gravity, you could say similar things. When gravity is important, when the self-gravity of the objects in your box is important, a uniformly spread out gas is not the highest entropy situation. And in particular, the way that I would put it is the thing about the Big Bang or the early universe that makes it low entropy is not that it's compact and dense, but that it's smooth. That is the weird thing with all of this gravity. And yeah, I think we agree on it. It's just a matter of choosing your right analogy. But the way that I like to highlight it is, as many other people have said, if you imagine a collapsing universe without fine-tuning so that the future state is special in any way, you could imagine a collapsing universe and all the current galaxies and photons, etc., would smush into a very small region, but it would be wildly inhomogeneous. It would be very lumpy. There'd be black holes in some places and empty space in other places, and that would be a high entropy state compared to the smooth state. And it's even trickier than that because the really high entropy state, even with gravity, is smooth. So gravity has this weird feature that when things are dense, that's when the local gravitational field becomes important. And under those circumstances, high entropy is not smooth. But as you know, from the Big Bang, the universe expands, right? And it dilutes. And if we're on the right track cosmologically right now, it might very well just keep expanding forever and become smooth again. But that will be a high entropy state in the future. So when you have gravity, you have this very complicated picture when high entropy, when it was dense, would have been lumpy, but it was smooth. High entropy, when it's very dilute in the future, is in fact smooth, just like you might expect.
So
I completely agree.
Okay. So Sean, at this point, do you have a preferred way of accounting for the apparent fine-tuning of the universe, or not really?
Well, you have to be a little bit careful because there are many different fine-tunings, and the low entropy of the early universe is one of them, and that's what we're talking about. And by the way, I think David and I will both agree, it is a scandal that modern cosmologists don't care about this puzzle as much as they should. Many of them don't
Leonard
even know.
Susskind does, right?
Some of them do.
Okay.
But there's a majority that don't. I think the number that do is increasing. I think that we're on the right track. But I think that given my various commitments to things, I can see two ways of getting a potentially natural low entropy early universe. One is pretty much the scenario that Jennifer Chen and I proposed almost 20 years ago now, where, like I said, if our universe expands and empties out, it will become a high entropy state and empty with nothing but vacuum energy, the cosmological constant in it. But if you can have quantum gravitational fluctuations in that scenario that pinch off an entirely new bubble of space that then grows into its own universe, that would be a way that this universe could increase in entropy even beyond the empty, what we call de Sitter space, the universe with nothing but vacuum energy in it. And so what you would have is a multiverse where, as you go into the future, you empty out, there's nothing going on, but there's a little quantum bubble that pinches off a little region of space that itself starts in a relatively low entropy configuration, but one with zero energy, zero angular momentum, zero electric charge. And then it explodes into, via inflation, a universe much like ours. So we could have arisen from a baby universe that just was a quantum fluctuation away from a quiescent parent universe. And the cool thing about the scenario is that if you run backward in time, the same thing would happen, but backward in time. Our universe was a baby universe coming out of a parent, but if you go far enough back, there were baby universes coming out backward in time. And so they would think that we live in their past. And so that's the scenario where time is eternal. There's no maximum entropy configuration of the universe. So as time goes on, entropy increases both to the far past and to the far future. The trick of that is having the way that entropy increases be to make universes like ours. That is the diciest part of that story. The other possible way that I can imagine it is if you don't believe that time is fundamental. The thing about the Schrödinger equation of quantum mechanics is there's no singularities or ends of time in the Schrödinger equation. Time is necessarily eternal as long as you're in an evolving universe at all. T in the Schrödinger equation goes from minus infinity to infinity. So that first scenario just lets that happen, where you can have time going eternally toward the past and the future. But there's a whole bunch of people who say, look, maybe time is not fundamental. Maybe the Schrödinger equation is only an approximation that is useful in certain emergent situations. In that case, you could imagine that if time is emergent rather than fundamental, and the space of quantum states, the Hilbert space of the universe, is finite dimensional, then this emergent time will only have a finite number of ticks on the emergent clock. So rather than time going from minus infinity to infinity, it goes from 0 to n, where n is some very large number. And then I can imagine that there's some extra law of physics that says at time equals 0, in this finite lifespan universe, the entropy was very low. I don't know what that extra law would be. I don't know why it would be there, et cetera. That's why I consider this a little bit less promising than the other way. But I think it's logically consistent with the idea that we are obeying the rules of quantum mechanics, but we start with a low entropy condition. So the way that I'd like to put the scenario that Jennifer Chen and I proposed is, to me, it is definitely the best scenario on the market, and it's a really bad scenario because I don't think that we understand the underlying physics well enough right now.
Let me just say one thing. And I'm very much of a fan of both of the lines of thought that Sean was just talking about. So both of the lines of thought that Sean was describing, I think, are very exciting lines of thought that very much deserve to be pursued. There's one thing to say a little further back in this discussion, which was as follows. When I was describing why people thought there's a problem about fine-tuning in the entropy case, okay, I said, look, on what I was calling a naive way of assigning probabilities to macrostates, the macro states associated with very low entropy are associated with very small probabilities. And this prima facie looks like it's a problem, okay? Looks like it's something that has to be addressed, looks like it's some kind of an emergency. But it also ought to be the case that whenever anybody tells you, oh my God, we've got a problem here because we've discovered that the actual situation of the universe as it presents itself to us is enormously unlikely, you ought to immediately take a step back, okay, and say, gee, that's a puzzle. How did you conclude that? It must be that you have intuitions about what's likely and what's not likely, then whose sources are something other than looking around at the actual universe which we find ourselves in, okay? And the first thing you ought to be saying is, where the hell did you get that? Okay. What other sources does this have to do with divine revelation? Does this have to do with some a priori reasoning about what's more and less probable? So the minute you hear something like that, you ought to be very skeptical. Okay. So it's my own view. And this connects with what Sean was saying at the end. If it turns out to be one of the fundamental laws of physics that we simply have to posit, okay, that the entropy of the universe was initially very low. And if somebody says, why did you posit this? The answer is because this gives us a probability distribution to which the world we see is a good fit, okay? The idea that you were once expecting an answer that somehow starts farther back than that is a little crazy, okay? Mind you, if Sean in his first proposal, in this baby universes proposal, has a way to avoid positing such a law, that's great, okay? I got no problem with that. Explanations should go, the deeper explanations go, the happier everybody ought to be, okay? But the idea, which is very widespread, I believe, in cosmology still, that there's some kind of crisis because we're faced with some situation where people think it makes sense to say, hey, here's what I'm worried about. The universe as it presents itself to us is highly improbable, is highly unlikely. The first thing that everybody ought to be saying is, that's a funny thing to say. It must be that you're getting your ideas about what's likely and what isn't from something in some other way than looking around at what happens in the world, okay? That you think you have some a priori idea about what's likely and what isn't, or you have some divinely revealed idea of what's likely and what isn't. You have something other than an empirically founded idea about what's likely and what isn't. And there's a lot to say about this, and I don't want to get into it too much, but everybody's first reaction ought to be, that's funny. Where'd you get that? Okay. And this bleeds a little bit into the conversation that Sean and I were having before about self-locating probabilities, because in the case of self-locating probabilities, there is an idea that you can get from a physical situation, I'm Kirk standing on the surface of the planet, by purely a priori reasoning to some assignment of probabilities, okay? And this has to do with why I was asking what frequency I need to measure in order to determine these probabilities and so on and so forth. I guess I come to these discussions with a very strong prejudice against other than empirical sources for saying the probability is this or the probability is that. And I think this has played a particularly destructive role in fine-tuning. Like I say, if Sean's, if Sean and his collaborator scheme works out about the formation of baby universes, making low entropy initial states more likely, that's fantastic. I think that's a great advance in our reasoning. that's quite different from, just as if somebody discovers something more fundamental than the Schrodinger equation or more fundamental than general relativity, from which either or both of those can be derived, that's going to be a fantastic advance in our understanding. But of course, it's possible that the Schrodinger equation or some relativistic field theoretic generalization of the Schrodinger equation is going to be a fundamental law of nature. And that's going to be fine too. And it might be a fundamental law of nature that the initial probability distribution is such and such. And for somebody to come and object, but that's highly unlikely, I'm just repeating myself here, I think always has to be greeted, at least at first, with some kind of puzzlement as to where these people are getting their ideas about what the probabilities are.
I kind of want to half agree with David here, and then and half push a little bit beyond, because I'm overall sympathetic with what you just said, but I think it's the thing is that physicists are often very sloppy in not only what they believe, but how they justify what they believe, right? And sometimes that sloppiness,
by the way, I'm dealing with my dog again. Sorry.
Okay. Sometimes that sloppiness is, innocent and forgivable, and we can fix it. Sometimes it's really hiding something that is problematic. In the case of the fine-tunedness of the initial conditions of the universe, it's a little bit unfair to just say it's completely non-empirical. After all, we think there are laws of physics. If we were just talking classical mechanics to keep our life easy, there is a measure given to us by the dynamics, uniquely a measure that is preserved by the dynamics. And the statement is that in that measure, the initial conditions we need for the universe would be very unlikely. And so therefore, physicists say the universe is very unlikely. They don't mean that. They mean that obviously the state of the universe is evidence that the early universe was not chosen randomly from that condition. Therefore, what? Therefore, there's some work to be done. And I completely agree with David that maybe the work to be done 1,000 years from now will turn out to be, yep, that was just the initial conditions of the universe. I guess we learned that. But as a working cosmologist, you want to also say, maybe it's a clue to some physical mechanism that makes it that way. So I think that even though they talk sloppily, it's hiding a pretty reasonable thought process underneath. The problem to me comes when they very blithely extend the same thought process not to the initial conditions of the universe, but to the physical parameters governing the laws of physics, like the vacuum energy or the mass of the Higgs boson or so on. There, we do not have some pre-existing theory that gives us a measure on the space of anything. All we're saying is that, I kind of like numbers that are order 1. I don't like numbers that are of order 10 to the minus 100, and that's basically it. Maybe you can try to do better, but we don't. And just to make this as vivid as I can, because I'm very much thinking about this right now, a huge motivation for building the Large Hadron Collider in Geneva was we think that the value of the Higgs boson mass is unnatural. It is 15 orders of magnitude lower than the Planck scale. And we invented many, many theories to explain why that would be the case in some natural way. And essentially all those theories predicted that the Large Hadron Collider would not only find the Higgs, but a bunch of other particles. It has not done so yet. So this should be, and the physics community is not quite yet woken up to it, I think, a wake-up call that particular sloppy reasoning didn't do well. And look, we spent $10 billion to build the LHC, and I think that was money well spent because we didn't know, and we are trying to discover things. But I would like to see our reasoning about what is natural and what is unnatural be put on much firmer ground than it actually is right now.
Let me just, so there's a mutual admiration festival going on here. I completely agree with what Sean says. Let me just add one remark. The path from the measure, the Lebesgue measure being preserved by the dynamics, okay, to the Lebesgue measure being the proper measure, over possible initial conditions of the universe, is just a non sequitur, logically speaking, okay? Yes, it's not that this measure came from nowhere, okay? It's not that it came from liking numbers close to 1, as in the case of the natural constants, or something like that, but it didn't come from any place that is, as a logical matter, okay? Any probability distribution whatsoever over classical initial conditions is perfectly logically compatible with the classical equations of motion, okay? It's true that the classical equations of motion preserve the Lebesgue measure, okay? Preserve a particular measure. That's
the Liouville measure, I think you mean,
the
right?
Liouville measure, sorry. That's interesting. That's that's an interesting mathematical feature of these equations. The idea that there's an argument that goes from there to it's likely that the initial conditions were equilibrium conditions or something like that is just not true, okay? Obviously, any distribution whatsoever, any mathematically definable distribution over initial conditions can then be plugged in to the classical equations of motion and evolved into the future to see what you've got. So, yeah, it is something people often say, it doesn't come from nowhere. I agree, it doesn't come from nowhere, but it doesn't come from a logically relevant place either here. It's a true mathematical feature of the classical equations of motion that they preserve this measure, okay? But that doesn't in any way impinge on the fact that you can combine any probability distribution over initial conditions with these same equations of motion and get yourself, a probability map over trajectories.
But I think this is where we disagree, because I think that, of course, I agree with all the statements you made, but I don't think that they're the point here, because it's not supposed to be some kind of logical deductive argument. It's supposed to be clues to being better physicists. And I think that the clue is, if we did have, on the basis of understanding the dynamics of classical mechanics, some measure, the Liouville measure, and also some coarse graining in that measure, like Boltzmann talks about, if we had found out that the initial conditions that we need to account for the observations and the sensibleness of the universe in which we live were generic or in a high entropy macro state in that measure, we would just say, okay, there's nothing more to be explained. We're not going to spend our time looking for a better theory. But when they look very rare and unlikely in that measure, we say, okay, maybe there is something more to be explained. Maybe there's some extra physics going on.
So there is a little bit of disagreement here. Once again, I'm always in favor of deeper explanations. Okay. If we can go deeper than the Schrodinger equation, that's great. If we can go deeper than the Einstein equation, that's great. Start with something simpler. Start with something more intuitively compelling that leads to those. And that's the spirit of what you and Chen did, it seems to me. But it's quite different to say, suppose somebody says, and this seems to me analogous to what people are doing who think there's really a crisis or there's something that must be, that must come in to save us. If somebody says to you, why F equals ma? Think of all the equations that the world or that the classical world could have obeyed, okay? Take any reasonable measure, I don't know what it would be, on the space of equations that things could have obeyed. Why exactly F equals ma? There's a crisis. This is fantastically unlikely, okay? I say, no, this is confused, okay? It's just not right to reason about, say, the likelihood of a certain set of fundamental laws of physics, the a priori likelihood of a certain set of fundamental physics, a certain set of laws of fundamental physics, as opposed to another set of fundamental laws of physics. I don't care what measure you put on the space of possible classical equations of motion. F equals ma, or the principle of least action, is going to be one of a huge set of possibilities. Does this constitute some kind of crisis? Does this show that a deeper explanation is required here? It doesn't seem right to me.
But I think this is exactly my point. F equals ma, we think, doesn't require a deeper explanation because it is very much in line with what we might have expected. If the right answer were F equals m times some coupling constant times a to the power 1.001, then people would be saying, wait a minute, I want to explain that 0.001.
Because
that's something I want to dig into.
I don't understand. I thought this is because 1.001 is not 1.
That would be surprising. That would suggest that it's 1 plus a correction, and that correction comes from somewhere, and I want to try to understand it.
Okay. So we do have a little bit of a disagreement here, I think. Yeah. Good.
Well, this general line of inquiry we started on a few minutes ago seems to point, for me at least, in the direction of Boltzmann Brains, which is where I wanted to get to. But David, speaking of divine intervention, and Sean, you said you were a bit uncomfortable with the situation you proposed with Jennifer Chen. And this is kind of like kicking a hornet's nest, I think. But I know you are both strong proponents of naturalism, and also that fine-tuning has been cited in many arguments for intelligent design. But is any part of you at all compelled to lower your credence in naturalism by these sorts of considerations, or not in the slightest?
By fine-tuning sorts of considerations, you mean? Fine-tuning is the best argument in favor of the existence of God, and it's a terrible, terrible, terrible argument.
Okay. I think that answers my question.
I don't know. I know of lots of arguments for the existence of God, so I'm not sure that's the best one, but I think it's a bad argument. Yeah.
If you play by the rules, just to put it like a little bit of more flesh on the bones, but very quickly, if you're going to play that game, I think you should play by the rules, which is you should say, here's my theory of God. Here is the cosmology that it predicts. And I'm going to be a good Bayesian. I'm going to update my credences on the basis of comparing that to the cosmology I observe. The idea that you would start from the existence of God and predict anything like our universe at all is kind of hilarious to me.
So enter Boltzmann Brains. And as far as I understand the problem, it's that fully formed brains with memories, feelings, etc., can spring into existence due to quantum fluctuations in space or particles moving around randomly in the vacuum during a state approaching thermodynamic equilibrium. And while this is predicted to happen exceedingly rarely, in a universe that has no end, like ours presumably has, these brains are still expected to spring into existence infinitely more often than those that arise naturally in the earlier history of the universe like ours, which makes it much more likely than that we're in fact Boltzmann brains than bona fide natural brains. Is this the correct gloss, or how you two would put the problem?
Well, it's not. I think that's close to the language in which the problem is often put. But I think the way you just put it is incoherent. Okay. That is the claim was that an argument can be constructed to the effect that we have good reason for believing ourselves to be Boltzmann brains, okay, or to be overwhelmingly likely to be Boltzmann brains. And the argument was just the one you just described. The argument would go, we have good empirical reasons for believing in such and such fundamental laws of physics. Those laws of physics entail that there will be many more Boltzmann brains in the history of the universe with my current phenomenal experience than there are what you naturally arising brains or brains that arose in the way we think is usual with that set of experiences. And it's therefore overwhelmingly likely if you apply elementary principles of self-locating probability, which we were talking about before, that makes it overwhelmingly likely that we are Boltzmann brains. This argument, as you just stated it, and this part I think Sean will agree with, this is incoherent, okay? Because if you find yourself concluding that you're a likely Boltzmann brain, one of the things you're committed to is that all the reasons that you think you have for believing that the laws of physics are what you believe them to be, your memory of textbooks you've read, your memory of experiments that were carried out that confirm this or that fundamental theory of physics and so on, those are very unlikely ever to have actually occurred. Okay, it's not so the idea that a story of the form, because I take these to be the laws of physics, because I have good reasons for believing that these are the laws of physics, I conclude that I'm likely a Boltzmann brain, is self-undermining in a very straightforward way, because the second conclusion undermines the first conclusion that leads to it. The second conclusion, that I'm likely a Boltzmann brain, undermines the claim that you have good reasons for believing that the laws of physics that predict that Boltzmann brains outnumber natural brains are true laws of physics. Okay, so that can't be the right way to do it. That seems to me incoherent. I think Sean agrees with this, but I'm curious to hear.
Well, I do agree, but I think that there's something even more incoherent that most physicists who talk about the problem are actually thinking, because nobody thinks that they are a Boltzmann brain. Okay, like we all recognize that. It's the reasoning given for that conclusion that is a little bit dicey. I think that what David just said is very good reason to say, if you have a theory that predicts you are a Boltzmann brain, or let's just say a Boltzmann fluctuation, okay, like a random fluctuation into whatever situation you want, currently given our macroscopic knowledge, rather than a traditional thermodynamic evolution from a low entropy Big Bang, okay? If your theory predicts that you should think that you are such a fluctuation, you should throw away your theory. That theory is not very good because, for all the reasons David just gave, it's self-undermining or cognitively unstable, as he has said before and I have borrowed. But there's an even more simple and more naive argument that I think is what most physicists actually give, because they have a specific angle on this way to deal with self-locating uncertainties in a multiverse, large universe context, which is to say, we should reason as if we are typical observers within this very, very large universe. Not typical observers conditionalized on our macroscopic situation, right? Just typical observers. So the usual argument given against Boltzmann brains is that if the scenario were true, in which there were random fluctuations and most observers that popped into existence were not even looking like us, but were literally disembodied brains floating in empty space, I can just look around and see that I am not a disembodied brain floating in empty space. Therefore, I have ruled out that scenario by data, okay? By experiment, by looking around. I think that argument is entirely bogus, because we should not assume that we are randomly selected observers from a probability distribution that includes observers very, very much unlike us. Therefore, I think that what the argument David actually gave is the right one. We should not exclude Boltzmann brain cosmologies, because if we were Boltzmann brains, we would see a very different universe. We should exclude them because there's no internally coherent way that we could live in such a universe given our data and make sense of it.
But so let me push back on this a little bit. I of course agree with Sean's objections to what he characterized as the more usual thought among physicists where we might be any of these observers. But and this connects up with the discussion we were having earlier about self-locating probabilities. I just don't think it's the case that that there's anything about adopting a theory according to which the vast majority of brains that are physically like mine are Boltzmann brains, either in any way suggests that I'm likely to be one, okay, or leads to any kind of cognitive instability or anything like that. And the reason I don't think this is because I'm not pulled by these same a priori intuitions that Sean is pulled by about what the probabilities are, about self-locating probabilities. Okay. So let me give you an alternative picture. Somebody presents you with a theory of the world. Okay. And you want to know whether this is a serious candidate theory. You want to know whether this theory is empirically adequate. Okay. What you're supposed to do, and I think all you're supposed to do, is ask yourself, does this theory support the existence of agents of the type I take myself to be? Okay. Agents who are reasoning properly about their environment, reasoning properly to conclusions about what the physical laws are, have good grounds for this reasoning, so on and so forth. And the answer in these Boltzmann, in the theories that we're talking about are, yes, I see how it can support agents like that. These agents will be supported early on in the history, shortly after the Big Bang, way before you reach equilibrium, and the period when there are many Boltzmann brains. I don't have, how shall I put it? Here's what's required. Here's what I take to be a crucial difference between something that succeeds as a skeptical scenario and something that succeeds as a serious candidate for a physical theory. Something succeeds as a skeptical scenario if it's the case that somebody says, prove to me that it isn't true, and you're unable to do that. Okay? The hypothesis that I'm a Boltzmann brain succeeds as a skeptical scenario. Okay? It doesn't succeed as a serious candidate for a physical theory, because a serious candidate for a physical theory entails an additional requirement. Not just that I can't prove that it's not true, but that the kind of universe this theory describes is a universe that can accommodate the existence of epistemic agents who might come to have good reasons for believing that that theory is true. Okay? These theories that have my brain in them, but also have lots of Boltzmann brains in them that are identical to mine right now. Does this theory accommodate the existence of epistemic agents who could come to have good reasons for believing that this theory is true? Yes, it does. There's one right there early on in the history of the universe, well before it reaches equilibrium and well before it's swamped by Boltzmann brains. The only thing that might make me resist that is some a priori conviction to the effect that I know what probability to assign to the claim that I'm this brain or that brain, given that I have no direct empirical evidence one way or another. I've never been able to understand the attractiveness or the reasonableness of these a priori techniques for assigning probabilities. So I don't see any cognitive instability. I don't see any obvious problem in adopting a cosmological theory which says that the overwhelming majority of brains that are in states like my brain is now in are Boltzmann brains sometime far in the future.
So I think this is good because this is a real disagreement. This is not a fuzzy disagreement. This is a hard one, and I think an important one, and it does put the finger on the self-locating uncertainty difference. So just to be super duper clear here, forget about brains, okay? Forget about fluctuations into a few kilograms of gray matter via that. No one cares about that. We're not those. We all know. The problem with these, and I think this was implicit in what David was already saying, the potential problem with a universe that is eternal and exhibits random fluctuations, like the thermal fluctuations of gas in a box, is not that these weird brains floating out there in the cosmos, but I can conditionalize on everything that I have seen about the universe. Like, I'm here, I'm in this room, I have data from the cosmic microwave background, okay? There will be an infinite number of those observers in the universe, okay? And of all of them, and I think it's just counting, like they are all in exactly the same epistemic situation. There's a complete symmetry between them. There's no way of saying that you're one or the other. And so to me, it's perfectly obvious that if that's the theory you have, you had better assign equal probability to being any of them. I have no reason to do anything else. But the overwhelming majority of those observers are going to look out at the sky tomorrow and it's going to be black. Because all of the photons that were coming their way were not really from the cosmic microwave background and from stars and like that. They randomly fluctuated into existence. And so if you really believed that theory, that's the prediction you should make. But you don't really believe that theory for various reasons that I would argue come down to cognitive instability. But I do think that this is why it is crucial to have a strategy for dealing with these self-locating uncertainties. Jim Hartle, who just passed away, great physicist, and Mark Shrednicki wrote a series of papers where they said, I have a way of putting a probability distribution on these theories. Namely, there's probability 1 that I'm the good observer and probability 0 that I'm one of these bad ones that is going to see the microwave background disappear tomorrow. The problem with that is that they just made it up. There's no justification, no principled reason to do that, except that in their deeper heart of hearts, they don't really think that there are an infinite number of randomly fluctuated observers out there who will see the microwave background disappear tomorrow.
So this is a real disagreement. And look, here's very briefly and crudely how I would push back on this. There's how do I want to put this? What we do, it's a really important part of the way we evaluate theories that, here's crudely the story of science. You're thrown into the world, okay? You open your eyes, you start looking around, you develop something. Of course, this is a mythical object, but it's useful enough for purposes like this conversation. You develop what philosophers sometimes call a manifest image of the world, okay? This is the image of the world that you have prior to scientific investigation and philosophical reflection. I don't know it's what normally developing 5-year-olds believe about the world or something like that. It includes beliefs like tables and chairs continuously fill up regions of space, which we know they don't. They're mostly empty space, blah, blah, blah. It includes all sorts of things like that. And the story of science is basically you start looking a little closer, and two types of tensions develop within this manifest image. Various pieces of the manifest image come to be in tension with one another, and also various pieces of the manifest image come to be in tension with new empirical discoveries as you start looking more closely at the world. So I don't know what. You put a pencil in a glass of water, and it looks like the pencil is bent, but then you slide your finger along the pencil and it doesn't feel like the pencil is bent. And now you have two sensory reports, both of which you're used to trusting and putting faith in, and they're in tension with one another. And the manifest image is beginning to in very small ways come apart at the seams, and you have to figure out which of these to trust, and you have to develop a theory of optics which is going to explain why the pencil doesn't feel bent even though it looks bent, and yada yada yada. And you go on with this and on with this and on with this until, if things work out, you reach some sort of reflective equilibrium where you stop running into these tensions, okay, and then you're done, okay, and that's the way, that's the sort of idealized mythological way in which science is supposed to work. And what I want to emphasize here is that it's a very important feature of this kind of progress, that one of the things that's playing an important role in your theory choice is something that I guess that Quine used to call a principle of conservatism, okay? One of the rules here is that you don't depart more from the image of the world that you initially naively had. You don't depart from it in ways that are merely gratuitous. You don't depart from it in ways that are unmotivated. Okay, because it's one of the few things that you have to hang on to. You have other principles that you want: simplicity, elegance, explanatory power, so on and so forth. But this principle of conservatism is going to be a really important thing in limiting your theory choices. You want to be able to tell the story of all the decisions you made once the scientific project is done. Well, why did you decide this? Why did you decide that? Why did you decide that? And it had better be that none of the decisions involved departures from the manifest image which you weren't in some compelling way pressed to make, okay? Which weren't merely gratuitous, okay? And one of the most important and fundamental things you want to hang on to is that your ordinary modes of reasoning about the past, about what to expect from the future, so on and so forth, work, okay? And what you're going to be looking for in entertaining a theory of the world is to see if this kind of world can support the kind of epistemic agent that you take yourself to be. Okay, the one whose inferences about the past, like the Big Bang was 13 billion years ago and not 5 trillion billion years ago or something like that, is true, that these ordinary inferences that you make are, to the extent that the scientific theory allows it to be the case, to the extent that this achievement of reflective equilibrium allows it to be the case, are true. So that the right thing for you to do, the right attitude that you should take towards your scientific theory is, oh, if there are a bunch of brains or a bunch of rooms or a bunch of earths that I see in this theory, some of which are in important ways more like the one I take myself to live on than others, my attitude ought to be, that's probably me. Okay? The only resistance to that is this a priori faith in these principles of self-locating probability. And I think those are getting us in trouble here in ways that there's no good reason for them to do.
I'll just try to say very briefly, I don't think they're getting us in trouble. I think they're just letting us rule out theories where most people in my current epistemic situation would predict tomorrow that the microwave background will disappear. And it's easy to get rid of those theories. There are other theories out there. So it's just a helpful kind of way of choosing between theories. I think that in this universe, in this randomly fluctuating universe, I think it's a little wrong to say, well, there are people like me who are in the aftermath of the hot Big Bang. There's other people who think that they're in the aftermath of the hot Big Bang, but all of their experiences are just randomly fluctuating. And there's, by the way, way more of them than there are that are actually in the aftermath of the hot Big Bang. But I'm not going to count them. I'm just going to assume that I'm not one of them and get on with my life. I'd rather just throw away the theory as a whole.
Fair enough.
Well, this has been such a cool, special episode, and I really could not be more thankful to you, David, for coming onto the show for a fourth time now, and to you, Sean, for appearing in my corner of the multiverse. Yeah.
David only remembers 3 times because they've randomly fluctuated into his brain. We don't know. We can't rely on our records.
Well, thank you so much.
Thank you, Robinson, and thank you, Sean. This was a lot of fun.
Thank both of you. It was a lot of fun.
Hold on, Geeslings. Before you go, please like, subscribe, follow if you haven't already. Smash all those buttons. And also, if you haven't followed me on Twitter at Robinson Earhart, or if you're not joining me every morning as I eat my pint of ice cream on Twitch at Robinson Earhart on Robinson Eats, please do so.